knowing that it moves is not the same thing as knowing why something moves. And the why something moves, that's where we're getting into, and that is called dynamics. That is the topic of dynamics. And so here, we're really focusing on the cause of motion, which Isaac Newton really gave us this concept of force. And that's what we spent a lot of our time on Monday discussing. So we began by going over the catalog of forces, and I know this was kind of cumbersome, but there is a reason to this madness. We are about to, in my mind, go over the most important lecture of the entire semester. But all of this was building up to the lecture today. Because for us to do what I have in mind meaningfully, you do need to have a knowledge or familiarity that these things are actually in existence. So we looked at things like gravity, which is a force, the spring force, the tension force, the normal force, friction force, a generic push and pull force, drag force, buoyancy, thrust, and the electromagnetic force. Not only did we look at the names and the general idea of them, but I made sure to specify the source as well as the direction. And why I included those two descriptions or features in my descriptions will become very, very evident soon. So let's pick up from here. So we finished cataloging the forces. Now we can actually go on to utilizing them. So let's first speak about the key steps to solving dynamics problems. Now I'm going to do a little bit of a primer here and then come back towards the later end of the lecture to give a more fully developed one after we discuss a few different things. There's going to be a few essential parts. The first one is to identify the forces. Identify forces. And this here is going to be the key. This is what I believe is probably the most important thing that we can do, is to identify the forces. And for this, we want to identify the forces acting on the system. After you identify the forces, the second thing you're going to want to do are utilize what are called Newton's laws. So Isaac Newton didn't just give us the concept of force, but he actually built it out and gave for us mathematical descriptions that does represent reality. So these are going to be the two large steps. But identifying forces is step number one. And what do you know about step number one? If that is wrong, what can you say about everything else? It is all also going to be wrong as well. So we want to make sure that step one we know how to do very properly. So let's talk about how to identify forces. So let's say we want to look at all the forces acting on a person that's bungee jumping. So that's the rope. There you go. Person bungee jumping. We want to identify the forces on this object. The first step you want to do is to clearly define the object of interest. Clearly define the object of interest. Now what you want to do, you don't have to do it on paper, although I still do recommend you do it. But I'm not going to require you to do this on paper. But at least mentally, you should be drawing a line to distinguish whatever you're focusing on from everything else. So this is one of the first things that you need to do. Because if you don't know what you're talking about, then you're not going to know what you're talking about, right? That makes sense. So you need to first properly define the object of interest. Now, what this allows us to do is, if you look back on the catalog of forces that we made, you're going to see that there's going to be two groups. One are called long-range forces, the other one are contact forces. So long range doesn't require contact, and obviously the contact forces requires contact. By drawing this line around our object, you can clearly identify what are called the contact points. Identify contact points. And that we can do by simply understanding anything that crosses the line we just drew is in contact, therefore is a possible source of force. Now, if you want to identify the forces, these, of course, you need to be considering every single object that can potentially have it. So if we look at our bungee jumping example, what is crossing our line? Our circle, our red circle. The bungee cord. So there is clearly something going on here. And if you look on the catalog, we will call that to be tension. There would be a tension force from the bungee rope. Anything else crossing this line? Nothing else explicitly, but implicitly, there is air molecules that will be crossing the line, and that would be drag. So we want to name force and the direction. If you recall, tension force, now I wouldn't even memorize things like this because you just kind of visualize it. What direction will the tension force be acting? Tension? Right. If the rope is here, just imagine you bungee jumping, the bungee's, okay, if the bungee's pulling you down, you got on the wrong bungee. But the cord's going to be pulling you up, so it's going to be in that direction. Let's say at this point, you have reached the bottom and the person is now moving back up in this direction. The rope fully secured him and then now he's pulling back. That means which way is drag going to be? Drag is going to be opposite your motion and it will be down. Right? It's trying to keep you not moving. But this, number 3, is of contact forces. Like I mentioned, there is the second category, which is called the long-range forces. Name, force, and direction of the long range. These do not require contact. And do we have any of these forces in our bungee system?
Are you saying that drag is a contact force?
Yeah, the air molecules need to be there or else it won't slow you down. Gravity is definitely involved, and you will always have that as long as you're not in outer space. And gravity always acts down. And so these would be the steps to identifying the forces. Now let's do another example of forces on a rocket. So let's say that is our rocket. So the first thing you want to do is make at least a mental boundary around the object that you're choosing. Now, if you don't actually think about the interesting physics, you might be tempted to circle everything here as your rocket, but that would be a mistake. Because the exhaust is not part of the rocket. Instead, what you should have been circling is that right here. Now, what do you guys see crossing the line? The exhaust. So what kind of force is this?
Thrust.
Yeah, thrust force. And which direction is the thrust force? It would have to be up. The gas exhaust is down. The thrust force is opposite the direction of the gas exhaust, so it'll be up. Right? The thrust force is opposite the gas exhaust. What else is there? There would have to be drag, and it would be down. Those are the contact forces. Is there any other contact forces?
Gravity.
Well, gravity is a long-range force. There is gravity. And that would be it.
Meteors.
Huh?
Meteors.
Meteor? Oh, well, I didn't draw any on here, but if I did, yeah, those can make contact with the rocket. Yes. So that is to identify the forces. So that's step one. Let's talk a little bit about step two, the Newton's laws. Newton has three laws. He didn't just develop a concept called force, he actually worked out the details because he had to convince people that his theory was correct. So let's first talk about Newton's second law. This, I would say, is I don't want to say it's the most important, it's the most important for this class. We're going to be using this the most out of his three different laws. This law simply says the following: that the net force is equal to mass times acceleration. Here, M is defined as, well, the chemistry definition would be amount of matter in a substance. But this is a chemistry definition and is not entirely useful for us for physics. So instead, the more descriptive definition would be the resistance to acceleration. Resistance to acceleration. Meaning, you can apply a force by pushing on somebody. With the same amount of push you make, a lighter object will accelerate quicker. A heavier object will accelerate slower. That is what is meant by this mass, is resistance to acceleration. In response to the same force, a heavier object will accelerate less. Now, what this F net, this is defined as the net force on object. and this is defined mathematically. If you look at just the examples in the rocket, you have 3 different forces acting on the rocket. The net force, you would just add up all the contributions of those individual forces. So the net force would then be force 1 plus force 2 plus force 3, and so on and so forth. As many forces are acting on the object, you would have to add up all their contributions. Yeah.
Even if they're going in opposite direction?
Correct. And that's why it's in vector form. If one is going up and the other one's going down, you're still adding the vectors, but one of the y components is positive, the other y component is negative, so you would still be adding the 2, but they cancel out. Does that make sense? So, because if one is up, it would have, let's say, a positive, let's just call it A component. F2, let's say it's gravity and it's acting down, you would have, let's say, a negative G component. And so what would F1 plus F2 be then?
0.
Well, A minus G, right?
Oh,
Yeah, so it would be positive A plus a negative G in the J direction. And so you see how even though you're still adding 2 vectors, because the components are negative, it's still net subtracting.
Got it.
Now, luckily for us, there is a mathematical notation that says this, which is simply the sum of all the forces Fi. So the net force is that. So I'm sure you already memorized this equation because of its simplicity, but just in case, double box this, triple box this, whatever you need to do. So this equation tells us, this is the verbal form of the Newton's second law, an object with, or object of mass m subject to F net will accelerate with your acceleration vector A. That's what that equation tells us. Another thing that the equation tells us is that F net and A have the same direction. They have the same direction. Mass is just a scalar quantity. This vector and that vector has to have the same direction. It's just, in terms of the vector, it's just a magnitude that is different. Another thing to note is the object only accelerates with A with the vector A as long as F net is still being applied. The instant the net force stops acting on it, the acceleration goes to 0. Meaning the object does not have memory. That acceleration is only true as long as the force is acting on it. So the instant the force is not, then you get the acceleration to be 0. So let's do a conceptual question. What is the direction of acceleration? So let's say we have a box and there's 3 forces acting on it. There's force F1, force F2, and force F3. The magnitudes in this scenario are representative of the strength of each force, the magnitude of each force. So would it be up? Would it be to the left? Would it be down? Would it be diagonally up or diagonally down? Let's say that's A, that's B, that's C, that's D, and that's E. Who says it's A? Raise your hand. Who says it's B? Raise your hand. Who says it's C? Raise your hand. Who says it's D? Raise your hand. Who says it's E? Raise your hand. And E would be correct. That's because whatever F1 is doing, F2 is winning that battle. F2 is pulling in the opposite direction, so F2 is directly negating all of F1. But by the length of the arrow, you can see that F2 is stronger. So there's still going to be a downward acceleration. But you still have this sideways acceleration that's still there. So if we combine these two, there's still going to be, we'll call it F net of 1 and 2. It's still down, but there is still the F net 3. Sorry, not F net 3, just force from object 3. And so if you add the 2 vectors, you're going to get a F net in this direction. And we just discussed the net force and the acceleration have the same direction. That's why this is true. The net force has the same acceleration in the direction, at least, as the net force. So that's Newton's second law. Now let's go to Newton's first law. You guys may know of this in its verbal form, which is an object at rest will stay at rest, or an object in motion will stay in motion unless acted upon by an outside force. So it's an object at rest will stay at rest, or object in motion will stay in motion. Which is unless acted on by outside force. In this definition, object in motion, motion just means velocity not equal to 0. Velocity not equal to 0. Then it will stay in motion, meaning it will have that same velocity. It's referring to velocity. Sometimes this is called the law of inertia, but I just call it Newton's first law. Now, although words are much more precise than things like pictures and videos and such, they are not as precise as mathematical expressions. So let's develop a mathematical equivalent to Newton's first law. So mathematically, we get the following. If F net is equal to 0, then 1, velocity is equal to 0. That is, an object at rest will stay at rest unless acted on by an outside force. So if there is no outside force, what is the velocity? 0. It is at rest. Or the other alternative is to say that velocity is a constant, meaning it's in motion. It will stay in motion, meaning it will maintain that v if F net is equal to 0. That is a definition. Now, looking at these different categories allows us to define a few different scenarios. F net is equal to 0 corresponds to what is called mechanical equilibrium. In equilibrium, you guys should have in mind something that is not moving or something that isn't changing. And that is true, that's the general use of the word equilibrium. However, when we specify mechanical, we are actually saying the net force is equal to 0. That is what we're trying to specify. Now, on top of that, if velocity is also equal to 0, then we call it what is called static equilibrium. Static equilibrium. Static means not moving. And so that means the net force is equal to 0 as well as the velocity is equal to 0. But if it's constant, the velocity is constant, then we call it dynamic equilibrium. And they are given different names because you treat these two, static versus dynamic, you treat them differently. Because one is moving and one is stationary. Yeah.
So does that mean that static equilibrium and dynamic equilibrium are just types of mechanical equilibrium?
Correct. Correct.
Right, okay.
Yes. Static and dynamic are types of mechanical equilibrium. That is correct.
Thank you.
But this is Newton's first law mathematically defined. But let me remind you of Newton's second law. What is Newton's second law?
Force equals mass times acceleration.
Yeah, F net is equal to mass times acceleration. Let's compare Newton's first law to second law. Newton's second law gives us this relationship. If F net is equal to 0, what is acceleration then? It is 0. And if acceleration is 0, velocity is 0 or velocity is constant. So Newton's second law is actually a more descriptive version of Newton's first law. Do you guys see that? Then how the heck did Isaac Newton get credited with two different things just by doing one thing twice? How did he do that? Or, yeah, don't you wish you did that? You just do one thing and then everyone congratulates you for doing different things and not doing things. So clearly, we're missing something. And we are. Yes, Newton's second law is more descriptive, but it is Newton's first law that even defines what a force is. So what is a force? Anything that causes the velocity to change. After Newton defined force as anything that causes velocity, then he says, okay, I will give you the specific way in which velocity changes, and that is by this equation. So what Newton's first law actually does for us is it defines a force as anything that changes velocity. anything that can change velocity. That can change velocity. So if it can't actually change the velocity of an object, it is not a force. No matter how much you want to say that, these secular people who's into like witchcraft want to say like these spiritual forces are among us. No, unfortunately, they're not forces. So does anything that causes a change in the velocity, and Newton's second law is the more useful one that actually tells us, yes, but in which fashion? And the only thing that becomes relevant at that point in time is mass. You just need to know mass, and then you know the relationship between the force and the resulting motion. So with that, now let me ask you a question. So these are laws, right? Newton's first law and Newton's second law. Therefore, should always be valuable, or not valuable, always be valid. Is this correct? I see you shaking your head. Why? Because I asked it?
Yeah. You're a tricky guy.
Huh?
You're tricky.
What do you mean tricky? The answer is no. For it to be valid, Newton's laws, there must be a specific condition that is met. Newton's laws are valid only when they're valid. Now, of course, let's go over what that condition is. They are valid for certain reference frames. And that reference frame we call as the inertial reference frame. Inertial reference frame, which we will call IRF. So let's go over what this is. I said Newton's laws, or essentially Newton's laws, are what the entire dynamics section is about. So we need to know, when are Newton's laws actually applicable? So let's do that. Inertial reference frame, which we will call IRF. So let's do a series of thought experiments. So first, let me convince you of a scenario in which Newton's laws break down. Hopefully everyone has been in a car, but who has been in a car accident? Anybody? Okay, hopefully this isn't going to trigger any like PTSD, but think back to that car accident. Or if you haven't been in a car accident, maybe you've seen movies, and just try to visualize those scenarios. Now, when you get, the moment the car made the impact, you got dislodged from your seat. Is that correct? At least some way, shape, or form, or you tried to, but your seatbelt saved you, things like this, okay? So instead of using the word dislodge, which is very imprecise, let's use the words that are actually relevant to physics and actually have great precision. You would be accelerating with respect to the car. You guys follow so far? You used to be on the seat, but now because you are now no longer on the seat, or you're in a slightly different position, you must have accelerated at some point in time. But here's the thing. Was there any force acting on you? Or was it the car that experienced the force from the other car? Which one is it? In a car accident, did the car actually hit your physical body or the car that you're riding in? Well, hopefully no one got run over, right? That is a type of car accident, but we're talking about car-to-car collision. But there was no force acting on us. Therefore, laws are broken. Alright, so the rest of the semester is canceled because Newton's laws don't work. No. Obviously, the Newton's laws are not broken. So that would be the wrong conclusion. But just to finish this scenario, the car is what experienced the force. Not us. So if Newton's laws are valid, because we accelerated, we would expect there to have been a force on us. But if we just assess the scenario, we accelerated, but we didn't experience the force, that should lead to a conundrum. So that should hopefully lead you to the question, then how do we actually decide on this inertial reference frame? So how to decide proper IRF? Well, to answer this, let's do another thought experiment so that you guys can come to the conclusion yourself. And I just want to ask this question. Is a plane, who has not been on an airplane? Raise your hand. Okay, hopefully everyone has, okay. So is an airplane an IRF? That's a question. And the thought experiment that we're going to do is simply with a tennis ball. That is it. Let's say a ball is placed on the floor mid-flight. What's going to happen to the ball? In the middle of the flight, let's say there's no turbulence, it's one of those smooth rides, and then you just simply put the ball right in the middle of the aisle. What's going to happen? It's just going to stay there, right? Wait, Violet, why are you shaking your head? When you're mid-flight, smooth plane, no turbulence. Alright, the ball is going to stay at rest. But do you expect it to stay at rest? Is there any outside force acting on the ball? And the answer would be no, so this scenario checks out. However, let's consider a slightly different scenario. We're still in that same plane, but instead of mid-flight, let's say you place the ball on the floor during takeoff. What is going to happen to the ball? By takeoff, I mean you're still on the runway, but you're speeding up. You're going from rest to you're speeding up. What's going to happen to the ball? It's going to roll back. But was there any outside force acting on the ball? The only difference between these two scenarios is that one was in mid-flight, one was taking off. Every other circumstance was the same, but in one scenario, you have an inertial reference frame. In the other scenario, the ball begins to move, meaning Newton's laws were now broken. Acceleration, the ball is accelerating when there's no force acting on it. So what is the primary difference between these two scenarios? Because that will give us a condition for what constitutes an inertial reference frame. What is our primary difference?
Acceleration is at rest.
Huh?
Acceleration is 0.
Yes. This is IRF because acceleration is equal to 0. This is not IRF because acceleration is not equal to 0. When acceleration is equal to 0, that's when Newton's laws are valid from your perspective. Yeah.
Where do we get the conclusion that there's no force acting on the ball? Because wouldn't like the plane and
Yes.
gravity be acting?
Yeah, yes, okay. So no net force acting on the ball. No net force. So on the ball, you have gravity, but then the plane is balancing it out, and that's why, just like this cup, there's no net force.
Oh, so when net force is, wouldn't that just mean like net force equals 0, which is still applies to?
Yeah, net
Newton's-
force is equal to 0, so you would expect it to be at rest, right?
Yeah. Oh. I
Here,
see.
net force is equal to 0, you would expect it to be at rest, but it's doing what? It's rolling back. Clearly, Newton's laws are broken at this point.
Okay, that makes sense.
So Newton's laws are valid only when the acceleration in your entire scenario is equal to 0. So conclusion, accelerating frames are not IRF. Laws only valid when A is equal to 0. Does that make sense to everybody? Hopefully this thought experiment does make sense. But here's the thing. There is now alarm bells should be going off in your mind. Because where are we? Where are we? I don't mean TMU. I don't mean Los Angeles or whatever. But where are we? We are on the surface of the earth. And what does the earth do? It rotates, meaning if we are here, as the earth is rotating, what kind of trajectory are we making? A circular motion. You guys just had a problem set due. In circular motion, what are you always doing? You are constantly accelerating. What is that? Laws are not valid when you're accelerating. They're only valid when acceleration is equal to 0. So once again, class is canceled for the rest of the semester. No, I'm just kidding. No, there is a issue going on here. Earth is not an IRF. But it is considered to be negligible, and we will work this out together after the midterm. So we will verify later. And you guys will see that it actually does, at least the rate at which we are accelerating, it does have minimal effect. And so that we could use Newton's laws to pretty high accuracy. Yeah.
Actually, I'd like to understand how Newton's law is only valid when acceleration is 0, but then the second law that says F is equal to ma. So if A is 0 all the time, then F must be 0.
No. So the inertial reference frame is the viewpoint. So you could still have your box, and let's say the object of interest is the tennis ball. So the tennis ball can accelerate, and we can conclude that this acceleration will be associated with a net force. We're not in an inertial reference frame if the entire box is accelerating. That's what we mean by the inertial reference frame. So an object inside the system of interest, or the particle that you're focusing on, that can be accelerated. But your entire room that you're actually viewing it from, that needs to be in an inertial state, meaning not accelerated.
Right. So could it be moving with constant velocity?
Yes, at that point its acceleration is equal to 0. So that's why mid-flight, you could still do experiments in the plane. Yeah.
Right, got it, that makes sense. Thank
Yeah.
you.
Alright, so we'll verify this later and the negligible effects that it will have. Yeah, question.
In the thought experiment we just did, it's supposed to say if the ball is placed on the floor.
Yeah. Oh, place. Yeah. Yeah, that's correct. You gotta remind me after class. Yeah. All right, the next section. This is what I consider to be the most important section in this entire course. Not just this lecture today, but the entire course. And it is called the free body diagram, or FBD. It is so important. This is the primary reason why I delayed the entire midterm, because there will be a section just on this on the midterm as well as the final. Literally a section, just draw me this, or do this thing on the midterm as well as the final. It's going to show up on both things. Now, for those of you guys that hate the math, you guys will love this, because free body diagrams have absolutely zero math whatsoever. Everything is just conceptual. And the reason why I believe this is the most important thing is because this will tell me, are you actually understanding the physics? Not, are you understanding the physics and the math? Right? And a lot of the things that we've been doing so far, to get full credit, you need to understand the physics as well as the math, but not so here. In this is literally about, are you understanding the physics? And so for those of you guys that have been blaming your lack of math skills for your poor grades, well, this section will actually tell you if that was the only reason why. So let's define what this section is. And also, not only do I think this is the most important, for me this is, I think, the most fun topic in this class also. So, what this is a visual representation with objects as a particle. And shows all the forces acting on the particle. That's it. These are just, it's a diagram, it's a simple sketch. That's what it is. Let's talk about the steps before we go over an example. The first step is to identify the forces. We already did this step roughly 30 minutes ago, but I split it up like this because I do think it is the most important thing, and I wanted your guys to, or your minds to at least digest it for 30 minutes and then we'll come back to it, so that there will be at least some aspect of familiarity the second time around. So everything that we did in the identifying the forces, we're going to have to do again here. But the free body diagram takes it a little bit further. You don't always have to do it. It is of benefit to define a coordinate system. Thirdly, this is optional. You want to draw the F-net vector. So when you identify the forces, remember you're doing the naming as well as the direction. But you're going to be centralizing it on a point, or that particle. So let's see exactly what I mean. So let's look at an example of an elevator. So I know this is a very simplified one, okay, but this is the schematic that we'll be using. We need to identify the forces. What was step number 1? When you're identifying forces?
Name and direction.
Huh?
Name and direction.
No, before that. Yeah, you gotta at least mentally draw that little box around, okay? Because you need to know what is the object of interest. Clearly, the rope is not part of the elevator, and it would have been a mistake to include that as your object. This entire elevator, you're going to say, for simplicity's sake, you're going to say it's just existing at a single point here. And then you're going to identify all the forces and then draw it acting on this object. So let's do this. What are the contact points? Clearly, there's one right here. And that will be the tension. Right? There's a cable attached to the elevator, and there's tension. Which direction would it be pointing? It'll be pulling up. So we would be drawing the tension up. Anything else?
Gravity.
Well, contact.
Oh.
Contact. All right, well, let's do gravity. Gravity, yes, which direction? Yeah, gravity will be straight down. Oh, actually, hold on, I forgot to mention. Let's say it is accelerating up. Do we still want that gravity? Yes, the gravity's still there. Okay, the gravity's still there. Do we have any other forces? Any other contacts? Yeah, there can be drag, but here I didn't give you enough information to say which direction drag will be going. So you can say it's negligible or too ambiguous, something along those lines. So we'll say drag is negligible. Yeah.
What would you need to say in order for drag to be?
Okay, we'll do that example after we cover this example, okay? What would the net force vector be? If it's accelerating up, what would the net force vector be? What do you know about acceleration and the net force? They have to be the same direction. So the net force would actually be up. But this would be the free body diagram. This is going to be absolutely required, okay, for most of your problems in dynamics. Yeah, question.
Do you care about how long we draw the arrows?
No. So when you're drawing the free body diagrams, you don't know the length of the arrows because you're expected to calculate them. So you can't know it beforehand. So the free body diagram is primarily meant to show the direction, not the magnitude. But in certain scenarios, I can give you scenarios in which I say the length of the arrows are actually indicative of the magnitude. At that point, it is relevant. But when you're just generally drawing a sketch or yourself drawing a free body diagram, the length of the arrows is not significant. All right, let's do a similar example. Let's say it is accelerating down. An elevator accelerating down. And I'll give you guys 30 seconds to draw the free body diagram yourself. While I get a cup of water, I'll be right back. Alright, so let's do this example. So what does a free body diagram look like? Like I mentioned, you should at least be doing this mentally. You're not required to actually do it on the piece of paper. Okay. Let's come here. What forces are we in?
Tension.
Which direction?
Still, it's technically lowering it, but it's still pulling up on it. Keep it from falling, right?
So that. Any other forces?
Gravity.
Any other forces? Drag? Well, yeah, we'll say drag is negligible also. Any other forces? Ah, this is it. And this is why I'm saying free body diagrams are absolutely very, very important. This tells me if you actually understand the physics or not. Just because one's accelerating up and accelerating down, many of you guys are going to think something has to be different in terms of the free body diagram. No, that's not true. What is actually going on here? What is the scenario? You have an elevator, it's attached to a cable, that is it. You have an upward force from the cable, downward force from the gravity, that is it. The only reason why acceleration is up versus down is because the magnitude of the tension and the force is changing. One, you're pulling harder up, that's why it's accelerating up, but you can obviously lessen the tension, and this is like how you would be lowering someone down if they're trying to, go out of their windows to escape their parents or whatever. But this tells me if you understand the physics or if you're trying to just force the scenario to be different because you think it has to be different. Right? This becomes absolutely clear if you're understanding the scenario correctly or not. However, there is a slight difference in this optional free body diagram note. The net force would be down because it is accelerating downward. So note, free body diagrams are identical, but F net is different. So let's do another example. Skier pulled uphill. So I want the free body diagram of the skier. So let's say this is our hill. There is an angle theta. That is a skier. And he's being pulled up the hill. Oh yeah, question.
Oh, like on a quiz, would we have to say what direction the net force is going?
In most scenarios, no, but there may be problems where you're given this type of information, or knowing that might be of relevance to you, kind of like on a quiz next week or something like that. That's
but it's like not part of.
yeah, it's not part of, this is the free body diagram, and that is a free body diagram right there. So I'll give you like 30 seconds to try this one. Right. Free body diagram of the skier. So you need to make some decisions on what actually constitutes the system, or what is the object of importance. Yeah, question.
When you draw the forces, is it only left, right, up, and down, or can you draw?
No, it has to go into the correct direction. Alright, let's first define what our object is. Hopefully, you included the skis. Okay, the skis are important because the skis are moving with the person. Right, if you forgot the skis and you're wondering how come, why would you include the skis? My question is, why wouldn't you? If he was wearing clothes, would you not include the clothes? No, they're all moving as a one cohesive unit. Because they're moving as a group, all of that will be considered to be a single object. Now, when you start this problem, a few things to mention. You want to draw a line parallel to your surface. And the reason is going to be clear in just a moment. So let's start by defining that. And say that is our theta. Also, we want to draw our y-axis as well. So we want to say this is going to be our x and this is going to be our y. Right, it'll become clear in just a moment. So what are the contact forces? Well, what do you see in contact? The skier is in contact with what? Okay, with the rope, it's not in contact with the tension, it's in contact with the rope, and it will apply a tension. Which direction? Well, it would be parallel to the surface, and that is why you wanted to draw this coordinate axis. He's being pulled literally parallel to the ground. So you want to draw the ground parallel because that will be the exact direction of that force. What else is he in contact with? The ground. And if you look at your catalog of forces, how many forces are from the ground or caused by the ground? There's two. There's two. One is called the normal force, and it's always perpendicular to the surface, meaning it'll be going up straight in that direction. And once again, this is the reason why you wanted to make your coordinate axis, because it defines the directions for those corresponding forces. What's the other one from the surface?
Friction.
Friction. Oh, let's say he is being pulled up, that way. Hopefully that was clear. So then friction is going to be in which direction? it is parallel to the ground and opposite V. So the frictional force in this case would be backward, but still parallel to the ground. Anything else? Okay, gravity, which direction? That way? Incorrect. It is straight down. This is the force of gravity. Anything else? There is drag. If you gave this would be correct and incorrect. This would be correct as long as you specified drag is negligible. If you don't mention this, and it never shows up in your free body diagram, the only thing I can conclude is that you forgot to take that into consideration. At that point, that's a misunderstanding of the physics. But instead of having this, you could have had it over here and said drag would have been here, and that would have been completely fine. But if you don't want to show it on the free body diagram, you better have this description that drag is negligible is on there so that I know you took it into consideration. Forgetting to consider something is a absolute mental mistake, and that does have to be docked off points. Question?
How do you know when it's negligible or when it's
So if I don't ever say things like a strong wind or anything like that, then you could always assume it's negligible. Sometimes I'll just tell you it's negligible. But if obviously if there's a strong gust of wind, if you say drag is negligible to make your life easier, well, that would be incorrect. Because there was some indicator telling you that you should be taking that into consideration. Okay. So does that make sense? You need to consider drag some way, shape, or form. So, like I mentioned, this, you're just going to have an entire section on it on the midterm as well as the final. You see, there was literally no math, right? No numbers whatsoever. Although, no numbers is not necessarily no math, because, algebra. Yeah, pretty much no math in this section, and I believe this is the most important thing in terms of understanding the underlying physics. Because just, if you look here, you have to run through every single force, cause of force, and then make an intuitive decision. Is this relevant, yes or no? And that's why we did that painstaking catalog of forces, and we pretty much just, I don't know, it was kind of like a story time class where you're just writing my story down. Right? But we had to do that because that is what enables you to actually make wise decisions. Yes or no, is this relevant? Yes or no, is that relevant? Yes or no, you're making intuitive decisions. And that is what physics is about. So with all of this, let me go over the steps to the dynamics problem in a little bit more descriptive fashion. So steps to solving dynamics problems. So instead of writing, identify forces or anything like that, essentially I'm just going to write the overarching theme of assess the scenario. You need to know what system you're actually working with. This is the same thing as just draw for me a sketch in the kinematics section. Write down your knowns, givens, things like this. This, you're going to be required to sketch as well as the free body diagram. This is step number 1, or part of step 1. And of course, if step 1 is wrong, what else is going to be wrong? Literally everything else. Yeah.
You said sketch and the free body diagram. Is that like do you want us to sketch something separate?
Yeah,
from
this is a sketch. This is the free body diagram. If that makes sense. So sometimes I'll give you the sketch itself, at which point you don't have to. But if there's like a car going off or car collision or something like that, you might want to provide a simple sketch. Yeah. And this would be, listing things like your givens, knowns, and etc. It's just understand the problem that you are given. After you do that, you will always use Newton's laws. You don't want to use Newton's laws first because Newton's laws, remember what the second law is? It's simply the net force is equal to mass times acceleration. The free body diagram is going to tell you what your net force is. Free body diagram is an absolutely necessary step before you can even get here. And so it is pointless to begin with Newton's laws. You always want to start out with your free body diagram because you're trying to get the acceleration. Remember, dynamics is about what causes motion, but we still care about the motion itself. And so 3 would be everything that we've been doing so far in kinematics. Well, once you have acceleration, guess what you can do? You can calculate velocity, the position, through the kinematic equations. So here, we'll say kinematic equations. And like I mentioned before, this is why there will be no one-step problems. I can't even come up with one even if I tried. Because you always have to take an intermediate step getting the net force before you can go to the motion. You need to assess the scenario, that's step 1, and you cannot get directly to the kinematic equations because you need to know what your acceleration is going to be. And of course, within each of these, there's going to be smaller steps. And so that's why it's very, very simple to get to like 5 to 6 step problems. And that should be pretty much the standard. Now, we didn't get there yet, but we will also be using Newton's third law, but that will come much later. This is coming up. But we will not be using it in the midterm. Or no, we will not be using it on the quiz. Sorry. Any questions? Alright, well this is all I was able to get to in the calc-based class, and this is a pretty good stopping point. So we will end it here. As a reminder, projectile motion is going to be on the quiz tomorrow. I know the problem set was focused on circular motion, but I highly recommend going over projectile motion again because that is going to be still the dominating theme of the quiz tomorrow.